In lesson 90, we're going to prove 5 new formulas, which are very similar to what we did the other day with cosine of a plus b, tangent of a minus b, with all those sum and difference ones that we did. These double angle and half angle identities will let us get exact answers for the trig functions for some angles that are not multiples of 30s, 45s, 60s, and 90s all the way around the unit circle. So just some more tools to help us get exact values for some of the angles. So first we're going to do, for sine, cosine, and tangent, the double angle formulas. These will be the easy ones to derive. If I want sine of 2a, I always start out with what it is I'm trying to show. And I'm simply going to rewrite my 2a as a plus a. And now I'm going to use the formula for sine if I am adding two things together. That formula said we always take the sine, cosine, we keep the plus or minus symbol, and then we do cosine, sine. The angles always stay in the same order. So we have sine A plus cosine A sine A. Oh, wait a minute. Those are the same as each other. Commutative property, sine A cosine A is the same as cosine A sine A, so I can just add those together and say I have two of the same thing, 2 sine A cosine A. And that is our double angle formula for sine. And we'll put that in our formula list in a moment. Before we do our formula list, let's do the same kind of thing for cosine of 2a. So again, I'm going to start with cosine 2a, since that's what I want to prove. I'm going to rewrite 2a as a plus a. My formula for the sum or difference with cosine is always cosine, cosine, sine, sine. Always keep the angles in the same order. But with the cosine formula, the plus or minus sign switches. So now I have a minus in between. And then I step back and I look at that. Oh, cosine times cosine, that is just cosine squared. And sine times sine, that is just sine squared. So there's my formula for double angle. Cosine 2a is cosine squared a minus sine squared a. And you can go ahead and start your formula list with these. If I move on to the next one before you finish copying, don't worry, we'll come back to it for you to finish copying. Notice that the cosine 2a formula is really going to end up being more helpful to us in proofs because we get those squares and we have Pythagorean identities. And I put a box over this because I'm not going to have you write it down and memorize it. It's just staying there as a reminder. Then if I'm doing something with a proof, I could then change that to a 1 minus sine squared of a, and then keep my minus sine squared of a in there. Or I could keep the cosine squared of a and subtract and change the sine squared to a 1 minus cosine squared of a, and then distribute and go on and see where that gets me in a proof. So because of those squares, that cosine 2a is going to be one that we actually end up being able to use more than the sine of 2a, other than just evaluating new angles. In proofs, the second one will be more useful. Okay, let's go ahead and talk about tangent of 2a. And I'm going to derive this two ways. This one was specific, so I really have to follow the directions. This says I have to do it with sine of 2a and cosine 2a. With the identities, meaning those two identities that we just did. So I will follow directions. Tan of 2a, if I've got to use sine and cosine of 2a, I know tangent is always the sine of that same angle over the cosine of that same angle. Now I'm going to plug in the two identities we just proved, that sine of 2a is 2 times the sine of a times the cosine of a. And the cosine of 2a is cosine squared of a minus the sine squared of a. Much as we did the other day, we would really like to be able to start with a tangent right here. So to get that, I know that I would need to divide that numerator by the cosine of a. And that would give me a tan a where I see the sine a. And since I want just the tan a, I'd also need to be able to get rid of the cosine of a, which means I'd need to divide that numerator by another cosine of a. So dividing the numerator by cosine squared is the same as multiplying it by 1 over the cosine squared of a. But we know if we do that in the numerator, we must do it in the denominator. And it's not okay to only write it down once. We must show that we are doing the same thing to numerator and denominator. So we're not changing the problem. We're only multiplying by 1. Then we know we always need to write down the work because this is a proof. So if we do this, we get 2 sine a cosine a, and in the numerator we're dividing by cosine a and another cosine a. And then we divide the things, or we multiply both parts of the denominator by 1 over cosine squared a. So we get cosine squared a over cosine squared a minus sine squared a over cosine squared a. And then we look at what we've got. The cosine of a's cancel. The sine a over cosine a is the tangent of a like we wanted. And we've also got a 2 in front of that. And then in the denominator, cosine squared a over cosine squared a is 1. Sine over cosine is always tangent, but I have the squares in there. So it's minus the tan squared of a. And that's going to be our double angle identity. Tangent to a is 2 tan a over 1 minus tan squared a. Second way I could have proven that, if I did not have the specific direction saying use those identities for sine and cosine of 2a. If it was just totally my choice, I could have said tan 2a, and then the same strategy that I did with the sine and cosine identities for 2a, I could say that is the tangent of a plus a. And we have a formula for the tangent of a sum. It is the tangent of the first plus the tangent of the second, all over 1 minus the tangent of the first times the tangent of the second. And then if we simply take a step back and look at what we have there, oh, tan a plus tan a is 2 tan a over 1 minus tan a times tan a is tan squared a, and I got exactly the same thing, much shorter, but the way that I just did in green did not follow the directions. So read the directions, and it depends on what they say, what you do and don't need to show. So far we have these 3 identities. We now want to come up with some for sine of x over 2 and cosine of x over 2. So let's suppose I wanted the sine of 22.5. I know 22.5 is half of 45. So those are the kinds of angles I'd like to have these formulas for. Now, notice in the sine and cosine formulas, well, the tangent one also, I have an A and I have a 2A. A is half of 2A. So I want to get just sine of something that's the half. So if I think of this, sine of this A, that's half of the 2A. This I could isolate sine A. I could do some subtracting and dividing and then square roots to get just a sine A. However, this one is going to be a lot harder to get sine A or cosine A by itself because they're being multiplied instead of the square. So for both of these next two identities, I'm going to use my cosine 2a formula in my proof. So let's give these last two a try. So sine of x over 2. First thing I'm going to do is to pick some variable they did not already use. They've used x. So I can pick anything else. I'm going to pick a, since that's what I just did my formula with. And I am going to let a be x over 2 so that I can go back and use that one of those formulas I just did, and then I'll get back to the x over 2 later. That also means that 2a is equal to x. So anywhere I want in my proof, I can do that substitution for either one of those two lines. Now I told you I'm going to start out with the formula for the cosine of 2 times a variable, but I'm going to use 2a because I'm not using the same variable that I had in there. And we just wrote down that our formula for the cosine of 2a is cosine squared a minus sine squared a. Now these two half-angle identities are going to be different from all of our other trig proofs. For these two, we write down that cosine 2a identity, and then we are going to simply simplify things, which doesn't change it, just writes it in a different form, and or do the same thing to both sides. So it is not going to be side 1 equals, equals, equals until we get to side 2. It's going to be side 1 equals side 2. Simplify or add the same thing on both sides or multiply the same thing on both sides. We're going to have one equation below an equation, another one below that until we get what we want. So for this one, I know I want to get sine by itself. So I want to keep sine in here, and I'm going to change cosine squared to something that means the same thing. So it may not really be making it simpler, but it's replacing with something that means the very same. We know that cosine squared is 1 minus sine squared a. So I replace that, and I keep the minus sine squared a the same, and this time I'm keeping both sides all the way down, so that equals the cosine of 2a. Then I notice that I have minus sine squared a minus sine squared a, so this side is really 1 minus 2 sine squared a. So that's just a simplification. Didn't change anything. Okay, now I'm going to try to get sine by itself. So if I get rid of the 1, I subtract the 1 on the right, and I had to do the same thing to the left, so I have cosine 2a minus 1 equals the minus 2 sine squared a. And then I'm going to divide both sides by negative 2. But we don't really like having negative numbers in denominators, so I'm going to change this left-hand side to 1 minus the cosine of 2a over positive 2. And that is sine squared of a. So if I want just the sine of a, I've got to take square roots, which means plus or minus has to go in there. So my left side is plus or minus the square root of 1 minus the cosine, but 2a is x, so that's just x over 2. And on the right, I'm just going to have the sine of a, but a is x over 2. So there is my half angle identity. So if I'm trying to get the sine of 22.5, I could change that to, oh, that's the sine of 45 divided by 2. And then I could plug into this formula to evaluate it. The plus or minus will depend on what quadrant is this thing I'm trying to find? I'm trying to find the sine of 22.5. Oh, that's first quadrant, so I need to pick the positive one. But if I'm trying to get something that's in another quadrant, I'll need to pick the negative one, and I'll model that when we do a couple of examples after we derive our final identity, the one for cosine of x over 2. But any questions on this one? Okay, then doing cosine of x over 2 now. This is going to be very, very similar to what we just did. I don't really want to work with that fraction until the very end. So they've used an x. I'm going to pick any letter that's not an x. So I'm going to say a is x over 2, which once again means 2a equals x. When you are going through and deriving these, you write those two things down in your box every time the book asks you to derive it. We realize that the cosine 2a identity is the one that's going to be most helpful in getting cosine equals square root of something. So once again, we start out by writing down cosine of 2a is the cosine squared of a minus the sine squared of a. Make sure you do not turn that around the other way. Okay, I'm going to keep the left just like it is. This time I want to have cosines, since I am trying to get an identity for x over 2, that's what a is. So I'm going to keep that first cosine squared of a minus, I'm going to put parentheses around it so I don't forget to distribute the minus sign. Sine squared is 1 minus cosine squared of a. So if I distribute my minus sign, I have a minus 1, and then I have minus minus, so I have a plus cosine squared a, put that together with the one I already have, and I have 2 cosine squared a, and then the minus 1 on my right-hand side. That is still equal to cosine 2a, so I continue writing that down. I'm trying to get cosine of a, because a is x over 2. So I need to isolate cosine of a. So I want to get rid of the negative 1, so I add 1 on the right, and I add 1 on the left. That gives me 2 cosine squared a. So I divide both sides by 2, and I have cosine squared of a. To get just cosine a, I have to take the square root of both sides. So that becomes the plus or minus square root of all of that. So that means plus or minus the square root of 1 plus the cosine, and 2a is just x over 2, and that equals the cosine of a, but a is what I want. It is x over 2. And that is my final identity for the day. So here is our final list of all 5 formulas for you to get copied down. Sine of 2a is 2 sine a cosine a. Cosine 2a is cosine squared a minus sine squared a. Tangent 2a is 2 tan a over 1 minus tan squared of a. The half angle formulas look very, very similar. Have to choose plus or minus in both cases, depending on what quadrant the original angle is in. What are you really trying to find the sine or the cosine of? And then those 2 formulas look very, very similar, except for the plus or minus sign in the numerator. If it is cosine, we have 1 plus cosine x all over 2. But if it's sine, if we switch the operation between sine and cosine, that's the one where we switch the plus or minus sign, and we have the 1 minus cosine x over 2. And then all I have left for you today is I want to do a couple of examples and model how we do this. So I'm going to go on to those. Let me know at the end if anybody didn't finish copying these down and you'd like me to go back to this slide. But here is our first one that we're going to try to evaluate, the sine of 22.5. I recommend that very first you look at that and say, oh, 22.5. What quadrant is that? Oh, that's first quadrant. And in the first quadrant, sine has to be positive. So I'm going to say, and you probably do want to copy this down just to help you with that plus or minus at the very end so you don't get yourself confused. It is going to be, okay, write down, oh, I'm going to do that. 22.5 is the same as half of 45, and I know what 45 is. Because it is Q1, I'm going to pick the positive square root when I do the formula. The sine one was the one that did 1 minus the sine of just that numerator now, so just the sine of, that's cosine. That's what I was thinking, but not what I was saying and writing. So the formula is 1 minus the cosine of the 45 degrees all over 2. So they're both either 1 plus or minus the cosine over 2. When it's sine and we're switching to cosine, that's when we have the minus sign in there. One comment I did not make yet with these half-angle formulas, so these last two, we would never be able to leave it like this, the square root of a fraction. Square roots have to be where they have a rational denominator, so we're going to have to get to the square root of the numerator over the square root of the denominator, and if it is an irrational square root of 2, we'll have to multiply numerator and denominator by the same thing to get a rational number in the denominator. So let's see on this example what ends up happening as we go through this. We've now gotten to the point where we're ready to substitute in what we know. So we know this is the positive square root of 1 minus, and the cosine of 45 is root 2 over 2, and that's all over 2. Okay, before I worry about square root of the numerator over square root of the denominator, you know, I've got a complex fraction in there. Let me just clean up the fraction first, and then I'll worry about square roots. So I'm going to multiply numerator and denominator inside that square root by the least common denominator for all of my little denominators, so multiplied by 2 over 2 in this case, which means I have the square root of 2 minus root 2 all over 4. Now I'm going to take square root of the numerator, and it looks weird because we do have a square root inside a square root. That is okay. And then square root of the denominator, hey, it's no longer square root of 2. Square root of 4 is just 2, so I'm in good shape. So let's punch that in on our calculators just because we can. So let's do menu, where I can see a little more of it. Okay, so let's punch in. I think I'm going to extend that page and get that up a little bit higher. Sorry about that. So let's get our division fraction template in there, and in the numerator I want to do the square root of 2. I'm staying inside the square root, minus, I'm still inside the square root, I'm doing another square root, and then a 2, and then I'm going to go down in the denominator and do a 2, and I'm going to push enter. I was trying to find the sine of 22.5, so I am also going to enter on my calculator sine 22.5, and I get the same decimal. The problem is, what's on the calculator, I'm going to have to round. It's not exact, but the square root 2 minus root 2 all over 2 is exact. So anybody with a question on that one? Okay, one final example then for today. Let's evaluate the cosine this time of 165 degrees. So first thing, and you guys are going to write this in chat for me, first thing I want you to do is, which quadrant is that? And in that quadrant, will cosine be positive or negative? So I want everybody to type pos or neg into the chat. What are we looking for here? And hit enter. So excellent, this is going to be quadrant 2. So we've got our 165 degrees over here, and we know cosine's the x-coordinate, so it does indeed need to be negative. So I'm going to write down cosine of 165 degrees. Can I do that as half of something? Oh yeah, it's half of 330, and it must be something negative. So if you think about which quadrant first and write that down, that will help you not make the mistake with the plus and minus signs. Now we're simply going to put in our formula. It's always 1 either plus or minus the cosine of that new angle that's in the numerator over 2. And when it is cosine, it stays with the plus sign in there. So now all we have to do is keep our minus sign, plug in and evaluate. Now 330 is not in quadrant 2. 330 is over here with a positive cosine. That makes no difference because we're really finding cosine of 165, and we know cosine 165 needs to be negative. We know that the cosine for 330 degrees is positive, root 3 over 2. And then we're going to do the same thing that we did before. We're going to multiply that whole numerator by 2 and that whole denominator by 2 so that we can clean up the fraction. So we have that negative sign out in front. And then in the numerator, we have 2 plus root 3. And in the denominator, we now have a 4. So if we keep the minus sign, square root of the numerator, square root of the denominator, we have that as our answer. Now I'm going to do the same one a second way, using what we learned the other day. We could also write cosine as 120 degrees plus 45 degrees. So we could use our cosine for the sum of two angles formula, which was cosine of the first, cosine of the second, cosine, cosine, change from the plus to a minus sign. So cosine, cosine, sine, sine. Keep the angles in the same order. And I know all 4 of those. Cosine of, let's see, 120. That's right here. So that cosine is negative a half. Cosine 45 is positive root 2 over 2. Sine of that 120 is positive root 3 over 2. And sine of 45 is positive root 2 over 2. And let's combine some things here. So that, let's see, both of them have 4 now for the denominator. And so I have minus root 2 minus root 6. Those don't really look much like each other, but they are equivalent to each other. Punch them both in on your calculators right now and see what you get. See if you get the same decimals on those. And I'm going to let you guys do this one. And then you can also type in what were we finding with this cosine of 165. So type it in all 3 ways. Type it in like this, and like this, and you should get the same decimal each way if we wanted to have it rounded and not exact. I wanted to point this out to you guys because on homework sets, sometimes they will say, you do it this way. Do it as cosine 120 plus 45. Or they may say use the half angle formula, so you have to do it with 330 over 2. But they may not say, they may just say find it. Or on a test, I may just say use one of your identities and find it. And some of you will pick one way and some another way, and that's okay. There could be more than one form of the right answer. So give me a thumbs up. Are you guys all getting the same answer in there when you punch it in on your calculators? So far, so good. So anybody with questions today? I appreciate your attention as we've gone through these 5 proofs and examples.